Here's a quick check. At equilibrium, does a reaction go one way or both ways? 3, 2, 1. It is in both ways. Let's see why the beaker looks still, even though chemistry is busy inside. In this video, you'll learn what chemical equilibrium is, how to recognize a dynamic equilibrium, why a reversible reaction and a closed system often matter, and how to read real examples like dinitrogen tetroxide in equilibrium with nitrogen dioxide and liquid in equilibrium with vapor. Let's begin. Chemical equilibrium occurs when the forward and reverse reaction rates become equal. Concentrations appear constant because consumption and formation balance out at the same rate, not because reactions stop. Over time, reactants may drop and products rise, but once the rates match, both concentrations level off. That flat line signals equilibrium. Activity continues. Net change does not. Here's a classic case. Dinitrogen tetroxide dissociates into nitrogen dioxide, and nitrogen dioxide can recombine to dinitrogen tetroxide. In a sealed container, dinitrogen tetroxide and nitrogen dioxide react in both directions. When their rates match, the color stabilizes. However, equilibrium doesn't mean the reaction stopped. It's dynamic. Both directions still happen, but at equal rates, so the amounts stay constant overall. And it's not automatically 50-50. The final mix depends on the conditions, like temperature, pressure, or concentration, and on how the reaction tends to balance under those conditions. So far, we've covered that equilibrium has two opposing reactions: equal rates and constant concentrations. Curious how much you're remembering? Your personalized practice test, flashcard set, and study guide are all waiting for you. Just tap the link now and keep watching. Future you will thank you. The idea isn't limited to reactions. It applies to entire systems too. Let's zoom in on a closed system. In a sealed container, the liquid is in dynamic equilibrium with its vapor. Particles evaporate while others condense. When those rates match, the liquid level and vapor density look unchanged. On the other hand, if products escape, say a volatile vapor in an open beaker, there's no sustained reverse process. Without both directions available, a true equilibrium cannot be established. Many reactions are reversible to some extent, but under certain conditions, one direction dominates. We show equilibria with a double arrow to signal motion both ways. The single arrow usually means the reverse is negligible under these conditions. Let's practice with the two examples we've seen. In a sealed container, dinitrogen tetroxide and nitrogen dioxide reach equilibrium when the forward and reverse rates are equal. With liquid and vapor in an open beaker, vapor escapes. The reverse can't keep up, so it's not equilibrium, even if the color looks steady in the dinitrogen tetroxide or nitrogen dioxide system. If the rates aren't equal under the new conditions, it's not at equilibrium yet. So, to recap, equilibrium is dynamic. Forward and reverse happen simultaneously at equal rates, so concentrations stay constant. It requires a reversible process, often in a closed system. The dinitrogen tetroxide, nitrogen dioxide, and liquid vapor examples show the pattern clearly. Now that you've watched the video, let's see how much you remember. Head to the link in the description where you'll find Quizlet content made just for you.